Hello everybody, I'm going to speak about a new cathode material for advanced potassium-ion batteries. This is a polyanionic compound made of phosphate, vanadium and potassium. I chose to work on polyanionic compound because this kind of cathode material have reached a lot of interest due to their great structural stability and high energy density. The material that I work on have a specific stoichiometry which make it with a higher capacity. It has a monoclinic structure, a theoretical capacity of 150 mA per gram, an average insertion potential of 3.5 volt. It has, as I said before, a great structural stability, but as almost all the phosphate-based compound, it has also a low intrinsic conductivity. In order to enhance this conductivity, we have worked on the synthesis process. We have made a solution of all the precursors, and directly in this solution, we have added carbon sources in order to make a composite material. These carbon sources are graphene oxide or carbon nanotube. This solution with carbon inside is then injected in a spray drying chamber. In this chamber, there is droplets that are made, and due to the evaporation of the solvent, we obtain a powder of mixed precursor. 4 compositions have been investigated. Firstly, the pure KVP material. Secondly, the KVP with carbon nanotube. The KVP with reduced graphene oxide, and a mix of both. Here are some of my results. We have first analyzed the heat treatment in order to obtain the pure phases. We have set different temperature in order to see where the temperature is optimal to obtain the pure phases. And as you can see here, the optimal temperature is 650 degrees Celsius. Because higher temperature lead to impurity and lower temperature lead to a not a well crystallized material. We have also analyzed the influence of duration, and in this case, the optimal duration is 8 hours, because less than 8 hours lead to a not well crystallized material, and higher time lead to the same result than an 8 hours. We have also analyzed the influence of carbon addition on the purity of the material, and as you can see, there is no impurity that are present due to the carbon addition. After that, we have analyzed the influence of grinding on the purity of the material, and as you can see, the crystallinity is reduced, which is quite logical due to the grinding, but there is no peak of impurity in the diffraction pattern. We have then analyzed all the material in microscopy. As you can see, the pure KVP material have spherical shape. This is logical for spray drying process. When we observe the composite compound with carbon nanotube, you see that the spheres are flattened. This is due to the reticulating effect of carbon nanotube. For the graphene oxide composite compound, we have also spherical shape, and as you can see in the TEM images, you have the graphene oxide sheet that recover the particle. In the case of the carbon nanotube composite compound, you can see that the carbon nanotube are well dispersed between and inside the particle. Regarding the mixed composite, you can see that both effects are observed. After grinding, there is no typical shape that is present. We have smaller particles, which is what we desire when we make the grinding. After that, we have analyzed the electrochemical performance of all the material. First of all, before grinding. As you can see, the pure KVP material, represented by the black dot, show low specific capacity of about 20 mA per gram. Then when we add carbon inside the material, we have a huge improvement of the specific capacity of all composite compounds. The main improvement is the mixed composite, which reach about 90 mA per gram. This improvement is due to the reduction of electrical resistance as shown by electrochemical impedance spectroscopy. As you can see, the resistivity is hugely decreased when we add carbon. This effect is mainly seen in the composite compound with carbon nanotube. After that, we have tried to green the material in order to reduce the particle size. We have an efficient nanosizing of sample. We have obtained particles of about 100 nanometers. And as you can see, the effects are quite different because the material that showed the best specific capacity is now the carbon nanotube composite compound. And as you can see, we have reached specific capacity of about 100 milliampere per gram for this compound. This effect is not shown in the composite with reduced graphene oxide inside the material. Why did we observe this effect? Because we believe that there is a destruction of reduced graphene oxide layer, leading to a lower performance for KVP with reduced graphene oxide composite compound. And we have shown by electrochemical independent spectroscopy that the grinding step hugely increased the resistivity of the material with graphene oxide. Also, we can see that we have a great cyclability of the KVP carbon nanotube composite compound. To conclude, we have obtained a pure phase by a spread drying followed by the short-time thermal treatment for all compounds, including the composite compound with carbon sources. The carbon addition lead to higher electrochemical performance in all cases, and the grinding step lead to a huge improvement of the electrochemical performance of the carbon nanotube composite compound, but have a destructive effect of the reduced graphene oxide composite compound. I thank you for your attention.